Hello students, this is lecture number 20 and which is actually uh, about solving problem number 5.4. Okay. So, in the last lecture number 19, we solved just half of it. The problem is like this. So, there is a structure which is shown here. So, the first part has the uniform cross section, the other part has varying cross section. The first part has distributed load B, which is B equal to 10 Newton per meter. The second half does not have any B, however, there is a concentrated load given at the interface of these two sections at point B, and this load is P equal to 150 Newton. Both the ends are fixed. Okay. And area, variation of area within this region is given by A2 equal to 0.5 x minus 1 meter square. Okay. And E is given to the power 10 to the power 7, that is 20 megapascal, which is E is given. Okay. Also, it is required that you take 3 noded element in this region. So, one 3 noded element, and this region you have only 2 nodes. Yeah. So, this is a global number 1, 2, 3, 4 given, and we have to solve like this one. Okay. So, we have already done the first part. Okay. So, and that I have posted already. Okay. So, what we have done is here basically looked at just that element. Based on that, we have derived first we derive with the strong form. A strong form we know already, and then for this element the first part of the structure problem given, we derive with the weak form, and from there we formulated for 3 noded element. Okay. And we accordingly found out what is the shape functions. Then we found out basically the equation we put in the basically this is u and w in terms of shape function. Then weak function we found out in terms of those n's. Yeah. So, and then we wrote from the continuous system we have this discrete system, and where we have the stiffness matrix given, the individual the entries in the stiffness matrix is given by this in terms of shape function and the Young's modulus and the area, and then we found out the derivative of those shape functions, and then we found out those entries in the stiffness matrices. Okay. So, we calculated those matrix K11 for example here, and we tried to even do the integration using the Gauss quadrature, and we found exactly the same values basically. Okay. So, we also discussed some tricks how to quickly find out the stiffness matrices given that the sum of all the rows will be equal to 0 and so on. It has to be symmetric, and sum of rows the for like one row, the if you add all the elements or all the entries of the stiffness matrix should give 0, and that way also you can get information. Based on that, you need not evaluate all the entries, so you can actually guess or you can find out what is the logic behind that. That also I discussed, and for 3 noded element the general stiffness matrix also we derived, and then we force vector also we derived for this one. Okay. And we had the force vector. Finally, we put that in terms of the discrete system we get, where this is the weight vector which is multiplied with the stiffness matrix, and which is multiplied by the displacement vector. Here you have force vector. Since W can be anything, right. So, since W is arbitrary, hence you can get rid of this, and then you get the k times k1 times u1 equal to f1. Okay. And where f has two kinds of thing, one comes from the body force, the other comes from the end forces. Yeah, so this is how it looks like. Okay. So today in this lecture, this is lecture number 20, and we will continue solving this problem. So this is problem number 5.4, okay, and solution continued. Okay. Okay, so the second element now we have to consider now. So second element, and which looks like this, okay, like this one, okay, and here x equal to given as equal to 3, x b equal to 3, and x c is equal to 5. We have to take two node elements like this one, okay. Okay, and area varies as a equal to 0.5 x minus 1 meter square, this is what it is, and E is same as earlier, E is given to be 2 times 10 to power 7 Pascal, okay, and that is all. Yeah. So there is one force which is given here, okay. So either you can consider here or we can consider later on. So I will not discuss the force yet, since this is at the P is given at the boundary, right. So P equal to if you see the problem, P is given here, P equal to 150 Newton, but this is common to both the elements here. So hence I will not consider here, okay. You can also consider here, but I will discuss about that in later. So this is how we have this, and we can now consider the we can have the force. This will be F 2, and this will be also the force here, and this will be minus F. Okay, no, not minus, but okay, this will be F 2 1, okay. Okay. So given these forces, if these are the end forces, let us say, which is the displacements are not known here, that is what I am assuming, you know. So and accordingly we have to find out. Now it is a two nodal, yeah. So first thing what you have to do, I mean the first we will start with again I am taking a long route to actually derive start from the strong form from there actually, but once you know what you are doing, then you can do shortcut also. You can go whatever you know straight away, you can go to stiffness matrix, so you can solve it, you know. No need to go start from the weak form on, but I am just showing all those things as steps so that you can relate with chapter 3, 4, 5, all of them together, okay. So I will start with a strong form. Right. So we have a strong form, and we know it to begin with. A strong form remains the same for both the parts basically. So this is EA, then you have du over dx plus bx equal to 0. Here however, in this problem bx equal to 0, right. So there is no body force, you do not see any body force here. So bx will be 0. So what we have is just this part, and second thing is a is not constant. So ax equal to basically a2. So this is a2 basically, yeah. So a2 x is equal to 0.5 x minus 1 meter square. So this is, so we have a2 here, a is nothing but a2, e is a constant, e we have given as this one, okay. So that means our equation simply in this case becomes d over dx and eax, yeah, eax, we write like this one, then du over dx equal to 0, yeah, okay. And hence our weak form. So weak form becomes simply like this. We have E A d u over dx, and this will be from 3 to 5. Okay. W will also be there. Then minus 3 to 5, and we have d w over dx e a x, then du over dx, yeah, dx, and this will be equal to 0. Okay. So, or we have, so this in global coordinate system, because we are saying 3 and 5 and all. So, this is how it goes, or we can write it like this. This is W5, and then we have E E A du over dx at 5, x equal to 5, minus W3, yeah, and we have E A du over dx, x equal to 3, minus 3 5 dw over dx e a x du over dx dx, yeah, and this will be equal to 0. Okay. So, done. Now, we have to find out what is the test function basically, and from there we can go ahead. Now, so this is a 2 noded, right. So, we have a 2 noded element, and hence we have to construct it, and we know that how it should be. It should be n1 and n2. N1, this is if it is local coordinate system is 1 and 2, and the length is L, okay, L2, which is equal to 2 basically, yeah, and here we have N1 and N2, hence there will be 2 of them. So, N1 will go like this, this is what the N1 will be, and N2 will be something like this one. So, this will be N2. Okay. So, basically N1 is going to be 1 at node 1 and 0 at node 2, N2 will be 0 at node 1 and 1 at node 2. So, this is how it is going to vary. Okay. So, we can find out the expression basically. So, we know that we can go this way also, like if it is the local coordinate system, typically in this case you take x equal to 0 and x equal to L2 like this. Yeah, this is the local. Yeah, so this is the local coordinate system. Okay, this is for convenience, so that we can do this way, and accordingly whatever finally you have to evaluate this integration, right. So, and this integration, whether you do in global coordinate system or local coordinate system, still you will get the same value. These are integration only, right. So, accordingly we choose wisely. So, here the N1 we can, since N1 has the root, this one L2 is the root. So, we say N1 equal to x, we can say x minus L2, and there will be some constant here, right. So, which constant? So, when x equal to L2, this will be N1 will be 0, and this is correct, but when x equal to L1, x equal to 0, this value is 1. So, put x equal to 0 here. So, this becomes minus L2. So, you have to derive divided by minus L2. Yeah. So, the value will be minus divided by L2. So, simply this is going to be 1 minus x over L2 is N1. Similarly, we can get N2. N2 will be simply what you see here is you know that you can get from here also, right? Says you know that n1 plus n2 has to be equal to 1. Yeah, so because they are linear, so this is 1 and this is 0 here. So 1, this is 1 here, this is 0 here. So 1 here, both of them are half half, so 1, right? So it's a linear combination. So everywhere you sum them, it will be value will be 1 only, and hence n1 equal to this one, so plus something equal to 1 possible only when n2 is x over L2. So this is x over L2. Either you can do like this one or you can derive. So x, you know that n2, the n2 is 0 at x, so you will write just x here, alpha x will be the 1, and you know that n2 is 1 at L2, so you have to divide by L2, so you get n2. Like that also you can consider. So we got the shape function for this, the two noded element, right? Then you can write the test function ux as I equal to 1 to 2 n I and then u I. Yeah. So this is element number 2 basically, right? So basically what we are talking about, node 1 local. So this is 1 2 you are saying, so this is all local. So here we have u1, this is u2, right? And this is all we are talking about local. Yeah, so local node number is 1, local node number is 2. Finally, when we assemble it, there we have to see the relationship between local and global coordinates, and then accordingly we have to relate. Okay, so we have the test function like this one, and then weight function also will be similar, and this will be I equal to 1 to 2 n I and w I. Here w also, this is w1, this is w2. Okay. So again all these are in local. Now everything we are working in local only. Okay. So once we have that, we have to go back, put that in our equation. Yeah. So this equation, first one we have this. So let's w5. So what is the meaning of that? Okay. So this equation, the weak form can rewrite this one is nothing but f we wrote is, so Ea du dx as x equal to 5 is nothing but this is f22, basically that's what we wrote. Yeah, so this is f22. Yeah, and this will be equal to minus f12. So basically this same as earlier in the last, for the last element also with the same thing. So we get here w5 f22 plus w3 f21, that's what it will be. So we can write that, and then you have this term. Yeah, so weak formulation we write the final one here. So weak form, we have w5 f22 plus, yeah, plus w3 f21, right? So done, and then minus 0, okay, not 0 but it will be 3 to 5, okay, and then d w over dx Ea du over dx dx. Yeah, and that will be equal to 0. Okay, fine. So the next thing is we are going to write, put these things here and see what is the value of that. So w5 f22, what is the meaning of that? So first of all, w5, okay, so we are the local and global, maybe first we have to see. So, global is like this. Okay. So, this may be the global one. How it is going? This is going from 3 to 5, okay, x, yeah. Local, we can maybe we take something else, maybe xi or something, you know, that way it is you like you are not confused, right. So, let us say this is local and it gets from 0 to LE, L2, right, so equal to 2 basically goes like this, yeah. So, this is the relationship between the two, yeah. So, basically xi xi equal to x minus 3. This is the relationship, yeah, and hence you have d xi equal to dx, yeah, exactly like both the length is 2 in both the cases, yeah. So, Jacobian will be actually in this case 1 only. So, length of this equal to length of this, yeah. So, anyway, so this is the relationship. Accordingly, we have to transfer from one to the other because we are doing all the things in local thing, yeah. So, when we say in this one Wx, so W3 is equal to okay, so that really means like this, we Wx equal to 3 will be W xi equal to 0, yeah, okay, and that really means we know that this is equal to W1, okay. Then Wx equal to 5 is equal to W xi equal to 2 or LE. We know we are talking about W2, W1, W2, that only 2 points, right. Okay. So, that really means what? The global W3 and F22 will be equal to W1 no, this will be F21, sorry. So, F21, yeah, will be equal to W1 F21 basically, and then W3 sorry W5 and F22 equal to will be W2 F22, yeah. Okay, so these things, these two are we have solved already. Now, next thing is this one, yeah. So, F, so 3 to 5 and 3 to 5 and dw over dx, Ea du over dx will be equal to we can convert into xi basically, and this will be 0 to LE, yeah, and then we have dw over d xi, E a xi we have to convert to, then du over d xi and then d xi, and there will be some Jacobian. So, since dx equal to d xi, so the Jacobian is equal to 1 only. So, accordingly we can transform directly from here to here, yeah. So, actually dw over dx equal to dw over d xi, because the relationship between that is linear, they are just shifting, one coordinate system is just being shifted like this, yeah, like this one. So, hence we can write that way nicely, okay. Now, what we are going to do is we have n values, we have n. So, n is given by like this, if x in terms of x, So in terms of, actually we should have written in terms of xi here. So this is actually xi because x is going from 0 to 2. Yeah, so this is equal to xi. So we can write accordingly. So n1, what do we have is n1 is equal to 1 minus xi le, yeah, which is in this case equal to 1 minus xi over 2, basically le equal to 2, n2 equal to xi over le, which is equal to xi over 2. Yeah, so okay, so accordingly we can put these values here. So what do we get from here? D n1 over d xi will be equal to minus half, and from here dn2 over d xi equal to half. Put these values here, and we get from this we get 0 to 2 and minus half, then e, and then a will be 0.5, and then we have x minus 1, x minus 1. So but x minus 1 meaning we have to convert that into xi, right? So let's convert there itself. So this is the relationship, and we know that a a2 is equal to 0.5 x minus 1, and which is in meter square. Yeah, so we have to convert that this meter square, so we have to convert into 0.5, and x is equal to xi plus 3. If xi equal to x minus 3, so x equal to xi plus 3. So you write here, so xi plus 3 minus 1, which is equal to 0.5 xi plus 2. Okay, so done. Okay, fine. The same thing we are going to write there in terms of xi now, right? So 0.5 times xi plus 2, xi plus 2 is 0.5 times xi plus 2, then du times d xi. So du basically not du times d xi. No, here we should not have written like this one. Okay, so here dn over d xi equal to minus half, but what we have to write is dw over d xi. Okay, so this is wrong basically. So what I meant is has to be dw over d xi. Okay, and here we will have du over d xi. Okay, so d xi. Okay, okay, and which is equal to 0 to 2, and we will have basically like this. So we will have w1 w2 multiplied by here we will have b, right? We have bt times b, yeah, and then we have e value, then we will have 0.5 xi plus 2 value d xi, and then here you will have u1 and u2 like this one. Okay, yeah, why? Because you are going to put these in terms of, so if w is equal to, how you got it? So because w is equal to n xi n xi, so like this, I equal to 1 to 2 I and then ui. Okay, so So, basically the dw over dx becomes equal to I equal to 1 to 2 dni over dxi, sorry. So, basically the here we should have dxi, what I meant, okay. So, dxi, okay, times ui, okay, okay, and sorry, not u, this will be w, wi, and hence which is called b, basically this is equal to w1 w2 multiplied by here you get dn1 dxi dn2 dxi, yeah, okay. So, which is equal to, you call it wt times this one is b bt, yeah. So, which is equal to b times w, where b equal to dn1 dxi dn2 dxi and w equal to w1 w2 transpose, yeah. Okay. So, this is done similarly dw du over d xi, that becomes a b times u, yeah. So, b times u, that really means you will have dn1 dxi dn2 dxi and then you will have u1 u2 like this one, okay, done. Okay, so the next thing will be writing this one accordingly, right. So, we are going to write this and this. So, basically we already worked out this one, this becomes this one times this one, and this becomes this one times this one, and bt b becomes like is the inside this one. So, we have basically the whole thing we can write it as wt k u basically, right. So, same thing we can write, let us write here is equal to w t k u like this, where this is w t transpose, this whole thing is k and this is u, yeah. Okay, so, where k is given by, so this I just say how you get all those values. So, I spelled it out. So, we get k value. So, k will be equal to 0 to 2, then we have bt. So, b is nothing but, if you see here, we can compose b from here. So, you have dn 1 d is equal to minus half and this equal to half. So, bt becomes like this, minus half and half, yeah. So, accordingly you can write here, say will be equal to minus half and half, and this becomes minus half and half. So, basically this is b transpose, this is b, okay. And then you have e, okay. So, e you can take outside because e is constant, and then you have 0.517 sorry, x minus 1. So, in this case we have zeta xi, sorry, we have xi plus 2. So, we have xi plus 2, 0.5 times xi plus 2. So, xi plus 2, yeah, and you have d xi. Okay. So, we get E and times 0 to 2, yeah, and then we get there will be a matrix here. So, this multiplied by this multiplied by this multiplied by this multiplied by this, yeah. So, 2 by 2 matrix. So, you see minus minus plus, so 1/4 minus, so what you get here is like this, 1/4 minus 1/4, 1/4, 1/4, and then you have 0.5 and xi plus 2 d xi, and is equal to we can have everything outside. So, you can see 0.5 if we multiply here, so all becomes 1/8 basically. So, we can have E over 8, okay, and 0 to 2, and then we have 1 minus 1 minus 1 1, and then we have xi plus 2 d xi. Basically this one we could have taken outside also. So, we could also write like this, is equal to E over 8, 1 minus 1 minus 1 1, and then integral 0 to 2 and xi plus 2 d xi, and you can have now Gauss quadrature, but in that case you have it was from minus 1 to 1. So, you have to convert that. Okay. So, let us see directly how you get the value of this will be, if directly you calculate, becomes equal to E over 8, 1 minus 1 minus 1 1, and you have xi square over 2 plus 2 xi, and you have 2 0, right, and what you get is you put here and here both. Okay. So, you get 4 divided by 2. So, this becomes 2 plus here 2 times 2 4. So, 4 divided by 2 plus 4 becomes 6 minus 0. See, if this becomes 6. So, 2 times 2 is 4 divided by 2 is you get 2 here, 2 plus 2 times 2. So, 4 plus 2 equal to 6 minus 0. So, becomes 4. So, basically you get E over 2, you get E over sorry, this becomes 6, it becomes 6 E over 8, yeah, 6 E over 8. So, the value becomes 6 E over 8 and 1 minus 1 minus 1 1. Okay. Okay, this the value of this integration, we know this is 6, yeah. So, we have calculated, we found out this value is coming to be 6. Now, can we apply the Gauss quadrature? Okay. So, we can apply that. So, let us use Gauss quadrature. So, please note that this is page number 21. Okay. So, somehow it is more than 20 is not allowed. So, I have to start a new page basically. So, here although it says 1, this means 21. Okay. So, okay. So, this is a Gauss quadrature, we want to apply for this. So, we have 0 to 2, and you have xi plus 2, we have to integrate. Okay. How to apply that? So, it said we have to apply it we have to change in -1 to 1 format, then only you can apply that. So let us say our we have to write that in terms of -1 to 1, and from xi we have to change it to, let us say, let us call it lambda. Okay, so some lambda value, this function in some this is a function, right? So this function, let us call it is f xi here. So we have to write in f lambda, and there will be some j Jacobian coming into picture, and then we have d lambda, something like this one, right? So then we can apply that. So what is the function here? So first you see if this is xi, if it is 0, yeah, if it is 0, then we have lambda equal to -1, then you have 2, and this is 1. Yeah, so basically we can write lambda equal to xi -1. Yeah, you can write it like that. Yeah, so hence d lambda equal to d xi. So actually that tells you that there is a j equal to 1 simply, right? So okay, so basically this is tells you j equal to 1, Jacobian equal to 1. Why 1? Because this equal to this, and here we get d lambda equal to d xi, hence we have the value 1 here, so hence j equal to 1. Okay, so this, then if that is a correspondence, then we can have that tells you xi is equal to 1 plus lambda, and we will put this value here. So f xi becomes f xi is equal to xi plus 2 equal to xi equal to 1 plus lambda plus 2 will be equal to lambda plus 3 basically. Yeah, so we have lambda plus 3. Okay. Okay, so accordingly we can put this value here. So what do we get? We get, let's call this integral. So I will be equal to -1 to 1 lambda plus 3, yeah, and then d lambda. That's what the answer is. And what it tells you, the value will be simply is equal to 2 over the Jacobian is whatever the Jacobian is multiplied by the Jacobian has a 1 basically. So this tells you W1 into F1 f xi equal to 0, but xi is here actually means lambda here, lambda equal to 0, where W is nothing but 2. Yeah, we know that. Now only 1 point. So linear, this is linear, just 1 point Gauss quadrature can give you the exact solution. So we take lambda is equal to the W equal to 2, W1 so 2 multiplied by f at lambda equal to 0. So if it is 0, so it becomes 3 here. So 2 times 3 equal to 6. So we get the same value as earlier. Okay. So basically once we have that, what we found out is k is equal to 6 over 8, then E, and then we have 1 minus 1 minus 1 1. We got that. Okay. So so far our equation, if you sum them together, is basically the f we have W 3 sorry, this is W2 multiplied by F22 plus W1, and then we have F21, then we have equal to, is equal to, we have W1 times W2, and then we have, okay, so let's write like this one, is equal to nothing but W1 W2 and then we have 6 over 8 E 1 minus 1 minus 1 1 U1 U2. Yeah, so this is what we have, and we can write or W1 W2 we can have in common, and we have 6 over 8 E 1 minus 1 minus 1 1. Yeah, then U1 U2 is equal to F. So W1 multiplied by F21, right? So we write F21, we have F22. Yeah, okay. Now since W1 W2 are arbitrary, so this is arbitrary, means this is true for all W1 W2, and hence we get 6 over 8 E 1 minus 1 minus 1 1 U1 U2 is equal to F21 and F22. So this is for the element number 2. Okay, so this is for local. We have these, and these are for local coordinate system. So next thing is to assemble. So we get for these two elements, we got two equations. This is for element number 2. For element number 1, we have the equation, and that is EA1 over 6 7 minus 8 1 minus 8 16 minus 8 1 minus 8 7 times we have U 1 1 U 1 2 U 1 3 is equal to, here we have B naught over 3 F 1 1 4 B naught over 3 B naught over 3 plus F 1 2. Okay, and element number 2, we also have the this kind of equation, and which is like this one, E 6E over 8 6E over 8, and then we have 1 minus 1 minus 1 1, and then we have U I call it U1 and U2, but actually this has U2, the second elements. If you wrote 1 here, we write 2 here. Yeah, okay. So is equal to, and we have here F2 sorry, F1 2 F2 ones, actually F2 2. Okay, okay, and then we have to assemble it. Okay, okay. So the derivation of this part, we note that you may not get in the notes actually, so you have to see the video basically to actually see how we got this one. So notes we lost somehow. So this is now we have to relate it to the global stiffness matrix, and what you see, the global numbering, if you look at that, it was like this one. So we had like this. So this was 1 2, and then we have 3 here and 4 here. Okay, so accordingly, so we have to arrange it or renumber it. So if you look at this is 1 3 4, right? So local was 1 2 3 like this. Now we have 1 3 4. So accordingly we write here, this becomes 1, this is 3, this is 4. Yeah, similarly we have 1 3 4, and here we had 4 and 2, this we have 4 and 2. So accordingly we write here, this is 4 and 2, this is 4 and 2, and we have to assemble. So we have to see, we have to write these things. Now A1 is 0.1, this A1 is given to be 0.1. Yeah, so in the problem, so we have to multiply basically bit 0.1, so we can have 0.7, 0.8 and so on. Here E is in common and the 6 is outside, so accordingly we have to do E is common, so this becomes 6 over 8 here. So actually 6 over 8 is 3 over 4, so it becomes 0.75 basically, right? So this is 0.75 from here, this is will be accordingly we have to write there. Okay, so let's write it. Okay, so we will put common E, and all other things here we can write where A1 equal to 0.1 meter square, so we will have that. E we will have in common, and B naught is equal to 10 Newton per meter, so we can have this value. The other we will find out what to do. Okay, so we are going to assemble, we will make a big matrix. Yeah, so maybe like this one and like this, and here we will have U, this is global now, so U1, U2, U3, U4 and U5, not U5, 1. So how many nodes we have? Only 4 nodes. Okay, U5 will not be there. Okay, so not the U5, right? So not this one. Okay, so this is equal to, we will have F1, F2, F3 and F4. Yeah, so 1 2 3 4, 1 2 3. Okay, let's not write here because there will be some common thing as well. So if I write, the common thing will be, so in common we have E both the sides, so we have E here, so we can have E common. A1 we know is 0.5, so we can have just E there. Okay, so we write E here. Okay, and then we also write this is 1 here, 2 3 and 4. Okay, okay, accordingly we can write. Now we also have to see what is the meaning of U1, U2, U3 first. So these are all global. So in local the meaning is, so if you see here, this this is element number 1 and this is U11, U12, U13. Yeah, so this really means in global, the in global this is U1, so this is U1, this is U2, U3 and U4. Yeah, so that really means, what I mean to say is this actually U1, this is U2, this is U3. Yeah, and sorry, this is not that. Okay, nomenclature is okay. So we have U1 here, this will be U3. Yeah, so global is U3. Okay, so local is number 1, number 2, number 3, global is number 1, number 3, number 4. So we have U3 here, this is U4 here. Similarly, this one is local, we have U4 here. Yeah, so this is U4, and this is U2. This is U2. Yeah, so this is from local to global numbering, and accordingly it will match. So U4, and this is where this is the connection between the two elements, right? Okay, so if that is the case, accordingly we can, so 1 3 4, so U1 into 3, similarly we have to transfer into the corresponding rows. So let's see 1 1 1, right? So you have 1 1 here, 1 1 here, then we will have 1 1 2, 1 2 is not there. So 1 3 is here, 1 4 is there. So there is no one business here. So first row comes entirely from this one only. So we get 1 3 4 7 minus 8 1, but we have to multiply it by 0.1 because of A1 and 6 divided by 6. So 0.7, 0.6, 0.8, 0.1 divided, 0.7 divided by 6, 0.8 minus 0.8 divided by 6, 0.1 divided by 6, and so on. And that would be in 1 3 4. Okay, so 1 3 4, and we have values coming from the first one. So let's write in like this. Let's use different color for the two elements. So 1 1, so we get 0.7 over 6, 0.7 over 6. Okay, then we have 1, then 3 and 4. So here we have minus 0.8 divided by 6, and here we will have minus not minus but plus rather 0.1 over 6. Okay, done. Next is so this is done, 0.7 over 6 and all. Here we will have again 1 3 4 only, so minus 0.8, 1.6, minus 0.8, all divided by 6 we will have. So 1 3 4, and the second one is number 3. See, third row 1 1 3 4. So third row 1 3 4, and we have values minus 0.8 over 6. Okay, then we have 1.6 over 6 and minus 0.8. Okay, then we have number 4 goes like this. Okay, so number 4 goes like this one. So here number 4 1 minus 8 7. So 1 0.1 over 6, 1 minus 8, so we get minus 0.8 over 6, and 7, so 0.7 over 6. Okay, so we got from the first element, okay, and corresponding to u1, u3 and u4. Accordingly we have to write the forces F1 and 2, F1, F2, F3. So we can find out the value of force vector and all later on. So we are just assembling the stiffness matrix right now. Okay, so the next one, element number 2, now this we are done with. Now this is 6 over 8, that means 3 over 4 means 0.75. So 0.75 minus 0.75 minus 0.75 plus 0.75, and that is for 4 and 2, 4 and 2, we arrive to 4. So we have to write like 4 4 will be 0.75, 2 2 will be 0.75, and the 4 2 and 2 4 will be minus 0.75. So accordingly we can write there. So let's go there, and different color. So 2 2 and 4 4. So this is 2 and 2, 2 4. So 2 and 4, 2 and 4. Right. So this is so where we write, yeah. So 2 2 4 4. So 2 here. So we have this point, this point, this point, and this point. Here also we have to write. Okay, we have to add here. So 2 2 is 0.75. So write 0.75. Here also 0.75 minus 0.75 minus 0.75. Yeah, the rest will be all 0. So we can put the value 0 wherever no values are there. So we have 0 here, 0 0, that's it. So we got this stiffness matrix. Now u vector, you have u1, u2, u3, u4, but remember in the problem we had like this one, right? So we have this is fixed, so u1 equal to 0, this is u2 also equal to 0, this is fixed, and then you have u3 and u4 here. Okay, so u1 fixed, u2 fixed, hence our value will be u1 is equal to 0, okay, u2 also equal to 0, fixed, yeah, because of this and this. Yeah, so only we have this one to solve, this multiplied by 3 u3. We have to find out what is the value of this one, f1, f2, f3, f4. Okay, so that we will do. So f1 f equal to f1, f2, f3, f4, the force vector, and will be equal to, let's assemble it. So the first equation we have this b naught over 3, where b naught is equal to 10 meter per Newton per meter. So we can have equal to 10 over 3, basically 10 over 3 plus f11, 40 over 3, 10 over 3, but this will be in number 1, 3 and 4. So 1, 3 and 4 will be 10 over 3, 40 over 3, 10 over 3. Okay, so just write first. So 1, 3, 4. So 1, 3, 4. So we have let's use the same color code. So we have 10 over 3. Okay, then we have 40 over 3, then 10 over 3. Okay, and then there was some summation plus 1 f1 f11 f12. So let's write that in first and last one. So plus F11 plus F12. Got that. Now next is so we got that. Now next is this F21 F22, that is in 4 and 2. Yeah, so fourth one will have F21. So fourth is, so this is the second element, fourth. So number 4 is F21 and number 2 is F22. Okay, so this is what we got. Okay, so now what we see here, this is F11 and F21. So we are missing one thing. So far we have not implemented one thing, and that is that there is a force here, yeah, and the value of that force there is 150 Newton. So this is P equal to 150 Newton. So this we have not implemented. So this we have to add. Where? We have to add at node number 4. Yeah, this is global node number 4, means the last row we have to add 5. Add this P. You can think different ways. One way is to just look at this point, right? So you have, if you cut little bit left and little bit right, so how will it look like? This will be something like this. This is node number, okay, look this one. Okay, so we have P equal to 150 Newton. Okay, and left of it is coming from the first element, so the value will be F12. From the right we have F21. Okay, so basically this F12 and F21 both are at the same point. This is how they are. Those will be the forces acting, because the reactions basically, right? So the first element had this force outside, which was F12, and hence if you on this section we will have the opposite direction, right? Yeah, so okay, so I will make like this. So basically this is coming from where? It is coming from, so we have this kind of element, right? Okay, we are talking about from here. Okay, so this is the one which I am showing here. Yeah, so the left side one, if you see, we had a force here like F12. The right side one had a force here F21, right? So hence on this element we will have this same force acting, but in the opposite direction, right? And here also we will have acting in the, if force is like this one, here the force will be like this one. So if you see from the stability point of view, right, so all the forces in x direction has equal to 0, and hence you will have P plus F21. Here there is a mistake basically. So here this one Okay, just a minute. Okay, the direction of force here, direction of force here is also like this one only. Yeah, so if you see the forces were on the same direction, so this was not opposite like this one. Yeah, so the forces are here like F, and then you have F21 is like this one. Okay, so the forces, that means this what I have drawn this one here is not correct. So since this will not be like that, so we will have this force also opposite direction, and this will be F21 like this. Why? Because at the both the ends the direction of the force are the same basically, so hence here reaction on this, on a small element like this one will be also, both of them will be in the same direction. So now we can write summation of all force has to be 0, and then we will have P minus F12 minus F21 has to be equal to 0, and we have F12 plus F21 equal to P. Hence we have to write this equal to basically P only instead of writing like that. If there is no force, if there is no force applied here, then P equal to 0, so this will be 0, or hence you can write this equal to 0. Yeah, so but in this case there is a force P, so instead of this one we are going to write force P. Okay, so basically what we get finally, the answer, I'm mixing mathematics and physics as well, just so that you can also make it should make sense. And we have 10 plus 3 plus F11. So this is some kind of, you can say this is kind of some reaction basically. Yeah, so we can keep it like this one. Then we have F22, this is also kind of a reaction. So we can write like this also, this is a reaction at node 1, so we can write at reaction at R1. Here also this is a reaction at node 2, this will be R2. Then we have 40 over 3, and then we have 10 plus 3 plus we have P value, and P equal to 150 Newton. We write like this. So this is the force vector. Yeah, so this is basically this replaced with P, and P is 150, and we are writing like this one. So this will be what the force vector will be. Yeah, so what we know here is this and this one. Yeah, so if you see here the value, this is 0, this is 0, so we are going to solve this multiplied by this equal to F3 F4, F3 F4 is given. So and this is E value here. So finally our equation which needs to be solved will be like this. What? This will be 16 over 6, E will be common, 1.6 over 6 minus 1.26 minus 0.8 over 6, 0.7 over 6 plus 0.75. Then you will have U3, U4, and then after that whatever the force we get here, that will be there. So our equation to solve will be E. Okay, so E is given to be 2 times 10 to power 7 pascals, so we write that, and then we have 1.6, yeah, so 1.6 over 6, so let's see, so 1.6 over 6 minus 0.8 over 6 minus 0.8 over 6, then we have 1 or 0.7 rather, so 0.7 0.7 over 6 plus 0.75. So 0.7 over 6 plus 0.75. Okay, then we have u3 and u4 and will be equal to in forces we have 40 over 3, 10 over 3 plus 150. So 40 over 3, 10 over 3 plus 150. This equation has to be solved. So we get u3 and u4 will be equal to 1 over 2 times 10 to the power 7 multiplied by, we have to invert, and what we get here is, okay, so here we can have 1 over 6 also, we have 1 over 6 here, so 6 we can take common, yeah, so we can write 6 here as common taken out, and then we will have here 6 multiplied by 0.75. So this will be 4.5 probably, yeah. So this 6 times this is 3/4, so 3/4 of 6, 0.45. So 0.45 plus 0.7, 4.5, sorry, 4.5 plus 0.7, so 5.2. Okay, so we write 5.2 here. Yeah, this will be 5.2 here, and okay, so our values becomes we are going to interchange, so this becomes 5.2, okay, 5.2, and then opposite sign here, so it becomes 0.8, 0.8, and 5.2 is gone, so 1.6 will come here. Okay, and then multiplied by, we have done that, then now 40 over 3, and then here it will be 450, 450 plus 10, 460, so 460 over 3. Okay, so we get u1 and u2 like this one, yeah, that you can multiply, you can get the exact value.